Earth feels normal. We wake up on it. We build on it. We argue, create, destroy, and repeat our lives on its surface as if this place were an obvious outcome of the universe, a default setting, something that was always meant to be here. Because we are here, Earth feels inevitable. But from a cosmic perspective, that assumption quietly falls apart. The universe is vast, old, and largely indifferent to complexity. Most regions are empty. Most matter never forms stars. Most stars never form stable planetary systems. And most planets that do form are hostile, unstable, or short-lived. Earth exists at the end of a very long chain of unlikely events. Not one miracle, many. We tend to think of Earth as a typical planet because it is the only one we know from the inside. But when we step back and look at the conditions required for its existence, a strange pattern emerges. Almost everything about this planet sits inside narrow margins. Small tolerances, fragile balances, change a little, and the system collapses. Earth is not simply a rock in space. It is a system that has remained stable for billions of years in a universe that constantly disrupts stability. It has avoided extremes that destroy atmospheres, sterilize surfaces, or tear planets apart. That alone is unusual. Most planets do not enjoy long, quiet histories. They are reshaped by chaos, bombarded, heated, frozen, stripped. Many never get the chance to remain calm long enough for anything complex to persist. Yet Earth did. Not perfectly, not safely, but just enough. This raises an uncomfortable question. If the universe does not favor planets like Earth, and evidence suggests that it does not, then why is this one here at all? It is tempting to answer quickly, to say that given enough time and enough planets, something like Earth was bound to happen. That probability eventually guarantees outcomes like this. But probability alone does not explain fragility. Earth does not just exist, it persists. It remains within a narrow window where oceans stay liquid, chemistry remains active, and long-term change does not spiral out of control. That persistence is harder to dismiss. The more we learn about planets beyond our solar system, the clearer this becomes. Worlds are common. Earth-like worlds are not, and planets that remain Earth-like for billions of years appear to be rarer still. This does not mean Earth is special in a mystical sense. It means Earth is unlikely, and unlikely things demand explanation. Not necessarily a dramatic one, not a conclusion, but at least a willingness to ask why the universe allowed this particular configuration to survive when so many others failed. We are accustomed to asking how life formed here. But a deeper question comes first. Why did the planet itself endure long enough to make that question possible? Because when we stop treating Earth as the baseline and instead see it as an exception, the story changes. Earth stops being the starting point of the discussion. It becomes the mystery. And to understand that mystery, we need to step away from the surface we stand on and look outward at the universe that produced countless planets, yet so few that resemble the one we call home. The universe is not gentle. On large scales, it is violent, cold, and relentlessly destructive. Energy moves toward extremes, structures collapse, radiation floods vast regions of space. Stability is the exception, not the rule. Life, by contrast, is fragile. It requires balance, moderate temperatures, predictable cycles, chemistry that can repeat itself without being erased by catastrophe. When we compare these needs to the conditions most common in the universe, a stark mismatch appears. Most of the universe is empty space, close to absolute zero. Where matter does exist, it is often trapped in environments that destroy complexity faster than it can form. Near stars, radiation strips atmospheres. Far from them, chemistry freezes. Between them, nothing happens at all. Even stars themselves are hostile. Many burn too hot. Many are unstable. Some flare violently. Others change their output on timescales that would sterilize any nearby planet. The calm, steady behavior required for long-term planetary stability is not typical. And then there is gravity. Gravity builds stars and planets, but it also disrupts them. Orbits shift, systems destabilize. Collisions are common over cosmic time. A planet can exist peacefully for millions of years and still be destroyed by a single unlucky encounter. The universe does not protect complexity. It tolerates it briefly when conditions align and removes it without hesitation when they do not. This makes Earth's long-term habitability deeply strange. Not because life exists here, but because the planet remained hospitable long enough for life to become complex. That requires billions of years without extreme disruption, without runaway heating, without atmospheric loss, without orbital chaos. Those conditions are rare. Most planets fail early, others fail slowly. Many almost succeed, then collapse. Mars appears to have had water, atmosphere, and chemistry. It lost them. Venus may have once been temperate. It did not remain so. Countless exoplanets orbit too close, too far, or too erratically to ever stabilize. The universe creates planets easily. It does not keep them livable. This suggests an uncomfortable truth. Life-friendly conditions are not a natural outcome of cosmic evolution. They are not what the universe tends toward. They are temporary alignments within a system that generally moves away from balance. And yet, Earth persists inside this hostile context. It has avoided the most common failure modes. It has not frozen, burned, or been stripped bare. It has not been thrown into chaos by nearby stars or violent gravitational interactions. This is not because the universe is aiming for life. It is because Earth occupies a narrow pocket where destruction has been delayed. That delay is everything. If the universe favored life, we would expect to see stability everywhere. Instead, we see brief windows, fragile islands of order surrounded by overwhelming hostility. Earth is one of those islands, and that raises the stakes of the question. If the universe does not favor life, then Earth's survival is not guaranteed by default. It is not a baseline outcome. It is a special case, not unique in principle, but rare in practice, which means we need to look closer. Because the next mystery is not just that Earth exists, but where it exists. Its position in the galaxy should expose it to danger, radiation, chaos, instability. And yet somehow, it does not. That contradiction takes us outward, away from Earth itself, and into the larger structure that surrounds it. At first glance, the Milky Way looks peaceful, a vast spiral of stars, gently rotating, filled with glowing clouds and dark lanes of dust. From a distance, it appears orderly, balanced, almost calm. But from the inside, galaxies are dangerous places. Radiation surges from their cores. Massive stars explode without warning. Gravitational tides distort orbits over millions of years. Entire regions are bathed in energy that strips atmospheres and sterilizes surfaces. And Earth sits inside all of this, not far away, not protected by distance. right in the middle of a dynamic, violent system. By most expectations, this should be a problem. Planets too close to the galactic center face intense radiation, frequent supernova, and gravitational chaos. Planets too far out lack the heavy elements needed to build complex chemistry. Even slight shifts in position can dramatically change long-term survival. There is a narrow region where conditions are tolerable. Astronomers sometimes call it the galactic habitable zone. Earth sits inside it, but even that description hides how precarious this placement is. The zone is not a sharp boundary. It shifts over time. Stars migrate, orbits drift. The galaxy itself evolves. A safe region today may not remain safe for billions of years, and yet Earth has stayed within relative calm. It has avoided nearby supernovae close enough to strip its atmosphere. It has not been sterilized by gamma-ray bursts, events powerful enough to erase life across entire planetary surfaces. It has not been pulled into unstable orbits by passing stars. This is not because such events are rare. They are common on galactic timescales. The Milky Way has seen countless supernovas. Many planets were almost certainly lost to radiation, gravitational disruption, or slow orbital decay. Entire systems may have been erased without leaving a trace. Earth passed through this environment largely untouched, not because it was immune, but because it was fortunate. And fortune alone becomes harder to accept when it repeats itself over billions of years. Earth's orbit around the galaxy is remarkably uneventful. It avoids dense star clusters. It does not plunge through the galactic core. It does not wander into regions saturated with high-energy radiation. This quiet trajectory matters. Long-term stability is not just about surviving one disaster. It is about surviving millions of potential ones without encountering a fatal combination. The longer a planet remains stable, the more unlikely that survival becomes. Yet Earth has done exactly that, which makes its location feel wrong. Not wrong as in impossible, but wrong as in improbable. As if Earth is positioned in a narrow corridor where danger exists everywhere nearby, but never quite reaches it. This does not mean the galaxy was designed for life. It means life exists only where the galaxy fails to destroy it quickly. Earth is not protected. It is merely spared, and that distinction matters. Because if Earth's survival depends on remaining in the right place at the right time, then location alone cannot explain everything. There must be additional layers of stability working together, factors closer to home. The next question is no longer about where Earth is in the galaxy. It is about the star it orbits, because most stars do not behave the way ours does. Stars are not stable by default. They flare, they pulse, they change. Many of them behave erratically, releasing bursts of radiation strong enough to strip atmospheres and sterilize nearby planets. Some grow brighter over time, others fluctuate unpredictably. Many live fast and die violently. From the perspective of long-term planetary stability, most stars are bad neighbors, and yet Earth orbits one that behaves unusually well. The Sun is not large, it is not extreme, it is not dramatic, it is steady. For billions of years, its energy output has remained within a relatively narrow range, enough to keep oceans liquid, but not enough to trigger runaway heating. Strong enough to drive climate and chemistry, but not so violent that it tears systems apart. This kind of stability is not common. Smaller stars often flare aggressively, bombarding nearby planets with radiation. Larger stars burn hot and fast, shortening the window for any long-term complexity to emerge. Many stars change their behavior over time in ways that would destabilize planetary climates. The Sun has avoided all of this. It burns slowly. It evolves gradually. It gives Earth time. Even its lifespan is unusually convenient, long enough for complex life to develop, but not so long that the system becomes static and frozen. The Sun sits in a narrow category of stars that provide extended calm without extreme volatility, and calm is everything. Life does not require brilliance, it requires predictability. It needs cycles that repeat without drifting into chaos, seasons that return, energy that arrives reliably, not in destructive surges. Most stars do not offer this. Many planets may exist in habitable zones on paper, yet orbit stars that make long-term habitability impossible in practice. A single violent flare, repeated often enough, can undo millions of years of chemical progress. Earth has largely avoided that fate, not because it is shielded by chance alone, but because its star is unusually well behaved. This does not mean the Sun is perfect. It changes, it ages, it will eventually grow brighter, but it does so slowly, predictably, on timescale that allows systems to adapt rather than collapse. Again, we see the same pattern. Earth's survival does not hinge on one lucky condition, but on many moderate ones aligning at once. A star that is neither too violent nor too quiet, neither too short-lived nor too static. Too much energy would destroy stability. Too little would prevent complexity. The Sun sits between extremes, and that middle ground is rare, which makes Earth's position feel even more fragile. Because stellar behavior is only one layer of the system, even a perfect star cannot guarantee stability if the planet's orbit itself is chaotic. Planets drift, orbits shift, systems destabilize over time, yet Earth's path around the Sun has remained remarkably steady, and that stability raises the next question. Why hasn't Earth's orbit broken down? Planetary orbits look simple. A planet circles a star. The path repeats. Years pass. From a human perspective, it feels permanent, almost mechanical, as if once an orbit forms, it is set forever. But on cosmic timescales, orbits are fragile. Gravity is never a two-body problem. Every planet tugs on every other planet. Every moon adds complexity. Nearby stars pass. The galaxy itself exerts tidal forces. Over millions and billions of years, these small influences accumulate. Systems drift. Resonances build. Chaos slowly creeps in. Most planetary systems are not stable over long periods. Orbits shift, tilt, stretch, and sometimes collapse entirely. Planets can be thrown inward toward their star, ejected into interstellar space, or sent onto wildly elliptical paths that destroy any chance of long-term climate stability. This is not theoretical. We see it everywhere. Many exoplanetary systems contain planets packed dangerously close together, locked in unstable configurations. Others show evidence of past chaos, missing planets, tilted orbits, scars of violent rearrangement. Stability is the exception, not the rule. Earth should be part of this pattern. It orbits within a system that contains massive neighbors, gas giants with enormous gravitational influence, a moon large enough to matter, a star moving through a dynamic galaxy. And yet, Earth's orbit has remained remarkably circular, not perfectly, but stable enough. Its distance from the Sun does not swing wildly. Its axial tilt varies, but within limits. Its seasons change, but they do not spiral into permanent extremes. Over billions of years, these parameters have stayed within ranges that allow liquid water and long-term chemistry to persist. This is not guaranteed. Slight changes would have dramatic effects. A more eccentric orbit could freeze the planet periodically or trigger runaway heating. A chaotic tilt could erase seasons or create extreme climate swings. A destabilized system could end habitability entirely. Many planets likely experienced exactly that. Earth did not. Again, this does not point to design or intention. It points to a narrow corridor of outcomes where systems happen to remain quiet long enough for complexity to build. But corridors this narrow are hard to ignore, because stability over billions of years is not something that happens by default. It must be continuously maintained by a delicate balance of forces that do not cancel out, but also do not amplify into chaos. Earth's orbit is not frozen. It is controlled, gently constrained by the presence of other planets. Buffered by gravitational interactions that, rather than destabilizing it, smooth out extremes over long timescales. The same forces that destroy other systems appear here to protect. This kind of balance is rare. Too much interaction leads to chaos. Too little leads to rigidity. Earth sits in between, which means its stability is not just about where it is or what it orbits. It is about how the entire system behaves together, a network of influences that, against expectation, produces long-term calm. And even that is not enough, because orbital stability alone cannot explain Earth's unusually gentle climate history. There is another factor, closer and quieter, that plays a critical role in maintaining balance. Something that most planets do not have at all. A companion that should not matter as much as it does. And yet, it does. At first, the moon seems insignificant. A silent companion. A pale object drifting overhead. It feels decorative rather than essential. Easy to imagine Earth without it, unchanged, simply darker at night. But that impression is misleading. The moon is not just a satellite, it is a stabilizing force, and its size matters far more than intuition suggests. Compared to its planet, Earth's moon is unusually large. Most planets either have tiny moons that barely influence them, or none at all. A moon this massive relative to its planet is rare, and Earth depends on it. The moon acts as a gravitational anchor. It stabilizes Earth's axial tilt, preventing wild swings that would radically alter climate. Without it, Earth's tilt could vary chaotically over time, turning mild seasons into extreme oscillations. Long periods of freezing, long periods of overheating, rapid shifts that complex ecosystems could not survive. With the moon present, those extremes are dampened. The tilt still changes, but slowly, within bounds. Enough variation to drive long-term climate cycles, but not enough to destroy stability entirely. Again, we see the same pattern. Motion without chaos. The moon also influences Earth's rotation. Early in Earth's history, days were much shorter. The moon gradually slowed the planet's spin, stretching days and nights into more moderate lengths. This mattered for atmospheric circulation, temperature regulation, and the rhythm of life itself. Too fast, and systems struggle to balance heat. Too slow, and extremes dominate. Earth found a middle ground, and the moon played a quiet role in that process. Even the tides, often dismissed as a surface detail, may have mattered. Tidal forces created dynamic coastal environments where chemistry could repeatedly concentrate, dry, mix, and restart. These cycles may have provided conditions that static oceans could not. None of this requires intention. It requires timing. The leading theory suggests the moon formed after a massive collision early in Earth's history. A violent, unlikely event that could just as easily have destroyed the planet or left it sterile. Instead, it produced a stabilizing companion. One event. Many consequences. Most planets do not experience this outcome. A collision large enough to form a moon often leaves systems unstable or lifeless. A collision too small produces nothing of consequence. The range where such an impact creates long-term stability is narrow. Earth passed through it. And again, not perfectly, not safely, but just enough. The moon does not guarantee life. It does not create habitability on its own. But without it, Earth's long-term stability becomes questionable, which deepens the pattern. Earth's survival is not explained by any single factor. It is the result of many conditions aligning across different scales: galactic, stellar, orbital, and now planetary. And even with all of this, Earth would still be vulnerable. Because stability at the surface means nothing if the planet itself cannot protect it from space. Radiation does not care about orbits. Solar winds do not care about moons. There is one more invisible shield Earth relies on, a feature that many planets lose early and never recover. And without it, none of the previous coincidences would matter at all. From space, Earth looks exposed. A small, rocky world orbiting a star that constantly releases streams of charged particles. Solar wind moves outward at incredible speed, carrying energy capable of stripping atmospheres and damaging surfaces. Most planets cannot resist this for long. Earth can, because beneath its surface something invisible is still working. Earth has a global magnetic field, a protective bubble that deflects charged particles and shields the atmosphere from being slowly peeled away. Without it, the planet would look very different. Mars offers a warning. Once, Mars likely had a thicker atmosphere and liquid water on its surface, but its magnetic field weakened early in its history. As it faded, the solar wind began to erode the planet's atmosphere, molecule by molecule, over hundreds of millions of years. The result is a cold, dry world. Earth avoided that fate. Its magnetic field has remained active for billions of years, generated by the motion of molten metal deep within its core. This internal dynamo is not guaranteed. It requires the right composition, the right temperature gradients, and the right internal structure. Many planets never develop one. Others lose it early. Earth's field has fluctuated, weakened, even reversed polarity many times. But it has never collapsed entirely. Even during reversals, the shield reforms. The system recovers. That persistence is remarkable. Because a magnetic field is not just a bonus feature, it is a long-term defense. It preserves the atmosphere. It protects surface chemistry. It limits radiation exposure over geological timescales. Without it, oceans evaporate. Without it, air escapes. Without it, surface stability disappears. And Earth's magnetic field does more than protect. It interacts with the atmosphere in subtle ways, shaping how energy is distributed around the planet. It allows life to exist on the surface rather than hiding underground or underwater. It turns a hostile stellar environment into a manageable one. Again, this is not perfection. The field weakens at times. Radiation still reaches the surface. Protection is partial, not absolute. But partial protection is enough. And that seems to be the recurring theme. Earth does not survive because it is invulnerable. It survives because it remains just protected enough. The more we examine these systems, the more the margins narrow. Each layer of stability depends on another. Remove one, and the whole structure becomes fragile. A stable orbit is useless without an atmosphere. An atmosphere is temporary without magnetic shielding. Shielding requires an active interior. Earth has all three, and even that is still not sufficient, because protection from space does not guarantee that a planet can hold on to its air in the first place. Gravity matters, temperature matters, chemistry matters. Many planets with magnetic fields still lose their atmospheres. Others retain thick atmospheres that become lethal. Earth does neither. It holds its atmosphere and keeps it breathable. That balance leads to the next question. Why did Earth keep its air when so many planets did not? An atmosphere is easy to lose. Planets form with gas, but keeping it is another matter entirely. Gravity must be strong enough to hold molecules down. Temperature must be low enough to prevent them from escaping. Radiation must be limited enough not to strip them away over time. Most planets fail this test. Small planets lose their air quickly. Heat gives gas enough energy to escape into space. Large planets hold on to thick atmospheres that crush surfaces and trap heat. Others lose their atmospheres slowly, eroded by stellar winds and radiation. Earth exists in between. Its gravity is strong enough to retain essential gases, but not so strong that it becomes a suffocating world of dense pressure. Its temperature is warm enough to keep chemistry active, but not so warm that atmospheric escape accelerates uncontrollably. This balance is delicate. Too much heat and lighter gases are lost. Too little gravity, and the atmosphere thins. Too much gravity, and the atmosphere becomes hostile. Earth threads this narrow path. It holds onto nitrogen and oxygen, while allowing lighter gases like hydrogen to escape. This selective retention matters. It prevents the atmosphere from becoming chemically stagnant or dangerously reactive over long periods. Again, this is not automatic. Mars is only slightly smaller than Earth, yet it lost most of its atmosphere. Venus is similar in size, yet its atmosphere became dense, hot, and lethal. Size alone does not explain the outcome. Earth's distance from the Sun, its magnetic field, its internal activity, and its gravity all interact to preserve a stable envelope of gas. Remove any one of these, and the balance shifts. What makes this more striking is time. Earth has held a substantial atmosphere for billions of years, not unchanged, but regulated. Oxygen levels rose, carbon dioxide fluctuated, nitrogen remained dominant. The system adapted without collapsing. Atmospheres are dynamic. They evolve. They respond. They drift toward extremes. Earth's did not. It remained within a range where pressure, composition, and temperature stayed compatible with surface chemistry and long-term stability. That persistence is rare. And it is not just about air. An atmosphere moderates temperature. It distributes heat. It protects the surface from small impacts. It allows water to remain liquid. Without it, even a perfectly placed planet becomes sterile. Earth's atmosphere is not perfect. It has caused extinctions. It has shifted violently at times. It has nearly destabilized the planet more than once. But it always returned to a narrow band of habitability. This reinforces a growing pattern. Earth is not optimized for life. It is maintained just close enough to stability. And still, atmosphere alone is not enough. A planet can have air, gravity, and protection, and still fail to support long-term habitability if it cannot regulate itself internally. If heat builds up without release, if the surface locks into stagnation. Earth avoided that too, because beneath its surface, something else is happening. The planet moves, slowly, relentlessly, and that movement changes everything. Water feels ordinary. It covers much of Earth's surface. It falls from the sky. It flows, freezes, evaporates, and returns. Because it is everywhere around us, it is easy to forget how unusual it is on a planetary scale. Liquid water exists only within a narrow range of conditions. Outside that range, it disappears. Too cold, and it becomes ice, locking chemistry in place. Too warm, and it becomes vapor, escaping into the atmosphere or space. Too much pressure, and it behaves in unfamiliar ways. Too little, and it vanishes entirely. On cosmic scales, this window is extremely small. Most planets fall outside it. Many worlds are frozen solid, their water trapped as ice for billions of years. Others are so hot that water cannot remain liquid on the surface for more than moments. Some may have water deep below ground or beneath thick atmospheres, but surface oceans are rare. Earth sits precisely inside this window. Not permanently, not effortlessly, but persistently. Its distance from the sun allows temperatures where water can exist in all three states. Its atmosphere moderates extremes, preventing rapid evaporation or global freezing. Its gravity holds oceans in place rather than letting them escape. Change any of these slightly and liquid water disappears. This fragility matters because liquid water is not just a solvent. It is a medium where complexity can build gradually, where chemistry can repeat, combine, and explore possibilities over time. Solid ice slows these processes. Vapor disperses them. Liquid water allows patience. It allows reactions to happen slowly enough to persist, but quickly enough to evolve. That balance is rare. Even more unusual is duration. Earth has maintained liquid water on its surface for billions of years, not continuously in the same form, but without losing it entirely. Oceans have frozen partially, evaporated partially, shifted and changed, yet they never vanished. This persistence is striking. Mars may have had liquid water briefly, then lost it. Venus may have had oceans early, then boiled them away. Many planets likely pass through a water-friendly phase that lasts only a fraction of their history. Earth did not. It remained inside the window. Again, not perfectly. There were ice ages. There were warm periods. There were moments when the planet came close to global freezing or runaway heating. But it always returned. Liquid water did not define Earth's early history by accident. It survived because the planet's systems repeatedly pulled conditions back from the edge. And that suggests something important. Habitability is not a static state. It is a process, a constant negotiation between forces that push toward extremes and mechanisms that resist them. Earth keeps negotiating, which means water alone is not the explanation. The planet must have a way to regulate itself over geological timescales, to release heat when it builds up, to recycle material rather than locking it away permanently. Many planets cannot do this. Their surfaces stagnate, their interiors cool, their chemistry freezes into place. Earth did not stagnate. It stayed active, and that activity comes from something beneath the oceans and continents, something slow, invisible, and essential. The surface of Earth moves, not quickly, not dramatically, but just enough to keep the planet alive. At first, Earth's surface looks solid. Continents feel permanent, mountains appear ancient and immovable. From a human perspective, the ground beneath us seems fixed, stable, and unchanging. But this is an illusion. Earth's surface is not a single shell. It is divided into plates that drift slowly over the planet's interior. They collide, separate, slide past one another, and recycle the surface over immense spans of time. This movement is rare. Most rocky planets appear to have stagnant lids, rigid crusts that do not move. Heat builds beneath them with nowhere to go. Pressure accumulates. Eventually, the system either locks into inactivity or releases energy catastrophically. Earth does neither. Its crust moves just enough. Plate tectonics allows heat to escape gradually rather than violently. It prevents the planet from sealing itself shut. It keeps the interior active without tearing the surface apart. This balance is fragile. Too much tectonic activity would make the surface unstable, constantly reshaped by extreme volcanism. Too little would trap heat, shut down recycling, and slowly sterilize the planet. Either extreme leads to failure. Earth sits between them. This slow movement does something else that is easy to overlook. It recycles materials. Carbon is pulled from the atmosphere, locked into rock, carried into the interior, and released again through volcanism. This process stabilizes climate over millions of years. Without it, greenhouse gases would accumulate or disappear entirely. Venus may offer a cautionary example. Its surface shows signs of catastrophic resurfacing events, rather than continuous regulation. Heat built up until it was released all at once. The result was not balance, but runaway conditions. Earth avoided that path. Its surface changes constantly, but quietly. Continents drift apart and collide over hundreds of millions of years. Mountains rise and erode, oceans open and close. The planet reshapes itself without losing coherence. This movement also creates diversity. Different environments form: shallow seas, deep oceans, volcanic regions, stable continents. Chemical gradients persist. Nutrients are redistributed. Complexity finds places to grow. A static planet cannot do this. It may host chemistry briefly, but it cannot sustain it across deep time. Without renewal, surfaces become exhausted. Systems freeze into simplicity. Earth did not freeze. It kept moving. Again, not because it was designed to, but because the conditions happened to allow it. The right internal heat, the right composition, the right balance between rigidity and flexibility. Remove plate tectonics, and many of Earth's other advantages collapse. Climate regulation weakens. Oceans change. Atmospheres drift toward extremes. Earth's surface movement is not optional, it is essential. And when we step back and look at the pattern emerging, stable orbit, calm star, large moon, magnetic shielding, retained atmosphere, persistent water, active crust, a troubling realization takes shape. These are not independent features, they reinforce one another. Earth survives not because it excels in one area, but because it avoids failure in many at once. Each layer compensates for the fragility of the others. And this interdependence raises the stakes. Because if Earth's history is filled with systems that almost failed, then survival was never guaranteed. In fact, It came close to ending more than once. The planet has walked along the edge before, and that history of near collapse is the next part of the story. Earth's stability has never meant safety. Beneath the appearance of continuity lies a history filled with interruptions, sudden collapses, moments when the systems that kept the planet habitable nearly failed all at once. Life on Earth has not advanced smoothly. It has been interrupted repeatedly. Mass extinctions mark these interruptions, events so severe that most species vanished in relatively short periods of time. Not because life was weak, but because the environment shifted faster than complexity could adapt. Some extinctions were driven by impacts from space, others by massive volcanic eruptions, others by climate shift that spiraled out of control. Each time, Earth came close to losing its long-term stability. The most extreme example may have occurred early in the planet's history. Evidence suggests that Earth may have frozen nearly entirely, becoming a global ice world. Oceans locked beneath ice. Chemistry slowed to a crawl. The conditions required for complex life pushed to the edge of impossibility. This state did not last forever. Volcanic activity continued beneath the ice. Greenhouse gases accumulated slowly. Eventually, the planet warmed again. Ice retreated. Stability returned. Earth recovered. Later, enormous volcanic provinces flooded the atmosphere with gases, driving climate changes that erased ecosystems worldwide. Oceans became oxygen poor. Temperatures shifted rapidly. Life collapsed, and then rebuilt itself. Again and again, the pattern repeats. Earth approaches failure. Systems destabilize. Recovery follows. But recovery was never guaranteed. Small differences in timing, intensity, or feedback strength could have pushed the planet past a point of no return. A slightly larger impact, a slightly longer volcanic phase, a slightly weaker stabilizing mechanism. In many cases, Earth survived by narrow margins. This matters because it reframes habitability. Earth did not remain stable by avoiding catastrophe. It remained stable by absorbing catastrophe without losing coherence entirely. The planet bent without breaking. Most planets do not get this many chances. A single runaway event can end habitability permanently. Atmospheres are lost, water escapes, surfaces lock into extreme states that cannot reverse. Earth repeatedly escaped that fate, not because disasters were mild, but because recovery mechanisms remained active. Each near extinction tested the planet's ability to regulate itself, and each time the same interconnected systems responded: atmosphere, oceans, interior orbit, pulling conditions back toward a narrow band of stability. This suggests something unsettling. Earth's habitability is not a static condition preserved effortlessly across time. It is a dynamic balance that has been challenged repeatedly and nearly lost, which means Earth's continued existence as a life-supporting world is not just unlikely, it is contingent. It depends on a long sequence of recoveries that could have failed at any point. When we look at Earth's history this way, survival stops feeling inevitable. It feels provisional, temporary, dependent on feedbacks that have limits. And that leads to the next realization. If Earth has come this close to failure so many times, then its existence cannot be explained by a single lucky condition. It is the product of many rare factors working together again and again over billions of years. At some point, coincidence begins to feel insufficient, not because an answer must exist, but because the question grows heavier. How many conditions can align before we stop calling it luck? That question does not demand an immediate answer. It leads us toward something more subtle, toward how we interpret probability itself, and whether survival changes the way we count outcomes. One coincidence is easy to accept. Given enough planets, enough stars, enough time, something unusual is bound to happen. Probability allows for outliers. Rare events do not require explanation beyond scale, but Earth is not defined by one rare event. It is defined by many. A calm star, a stable orbit, a large moon, a persistent magnetic field, a retained atmosphere, long-lasting liquid water, an active moving crust, repeated recoveries from near collapse. Each of these conditions is unlikely on its own. Together, they become something else entirely, not impossible, but increasingly difficult to dismiss. The problem is not that Earth is rare. The problem is that Earth is consistently rare across multiple independent dimensions. These conditions did not arise from a single cause. They emerged from different processes at different times, governed by different physics. Stellar behavior does not guarantee plate tectonics. A magnetic field does not ensure orbital stability. Liquid water does not imply a large moon. And yet, all of them are present. Probability becomes uncomfortable when coincidences stack. At some point, it stops feeling like randomness and starts feeling like constraint. Not design, not intention, but a narrow corridor through which outcomes must pass to remain viable. Earth appears to sit inside that corridor. This does not mean the universe is fine-tuned for life. The vast majority of space is sterile. Most planets fail quickly or slowly. Most systems never align long enough to support complexity. But the fact that alignment is required at all is significant. It suggests that habitability is not a simple outcome of planet formation. It is a rare configuration that must be maintained against constant disruption, a temporary balance in a universe that tends toward extremes. And here is the crucial point. We are not surprised by Earth's existence because we are here. Survivorship biases perception. We notice the winning outcome and forget the countless failures that made it improbable. This is not irrational. It is unavoidable. But awareness of this bias does not erase the pattern. It only reframes how we interpret it. Earth did not survive because it was destined to. It survived because it passed through a sequence of filters that eliminate almost everything else. Each filter removes the majority of candidates. Few planets form in the right region of a galaxy. Fewer orbit stable stars. Fewer maintain stable orbits. Fewer keep atmospheres. Fewer regulate climate. Fewer recover from catastrophe. Earth passed every filter. That does not demand a conclusion, but it does demand caution. When too many independent conditions align, explanation becomes more subtle. Not a single cause, not a single miracle, but a recognition that outcomes like Earth occupy an extremely small portion of the possible space. And that realization changes the question. Instead of asking, why did Earth form? We begin to ask, why are we surprised at all? Because perhaps the only places where questions can be asked are the ones that pass the filters. Perhaps observation itself selects for rare outcomes. And if that is true, then probability alone may not tell the full story. It tells us how unlikely Earth is. but not how to interpret that unlikelihood. To understand that, we need to examine how observers change the way we reason about existence itself, which leads directly to the next idea, not about planets, but about perspective. At some point, probability begins to feel misleading, not wrong, but incomplete. When we look at Earth and count how many unlikely conditions aligned, it is tempting to ask how the universe managed to get so lucky, how chance could produce something so finely balanced. But that question assumes something important. It assumes that Earth was one possible outcome among many equally observable ones, and that assumption may be flawed, because we are not neutral observers. We can only observe a planet that allows observers to exist in the first place. Worlds that fail early, collapse into extremes, or never stabilize long enough for complexity to emerge, leave no one behind to notice them. They are silent. This creates a subtle selection effect. We do not see all planets. We see only the rare ones that survived long enough to ask questions. From this perspective, Earth does not look like a miracle. It looks like a filter, a result that appears special because everything else is excluded by default. This idea is often called anthropic reasoning, but the name is less important than the implication. It suggests that our existence biases our conclusions. We are surprised by Earth's rarity because we imagine ourselves as external observers sampling the universe at random. In reality, we are embedded within a very specific outcome, one that had to meet strict conditions to produce observers at all. This does not make Earth less remarkable. It makes our perspective constrained. Probability behaves differently when observation depends on survival. Events that allow observers will always appear overrepresented no matter how rare they are in absolute terms. This explains part of the pattern, but not all of it, because even within this framework, Earth's stability is extreme. Many planets may briefly meet some conditions, yet fail quickly. Earth did not merely pass a threshold, it remained within it for billions of years. Selection explains why we are here. It does not fully explain how long we stayed. This is where probability and selection intersect in uncomfortable ways. We cannot treat Earth as a random draw, but we also cannot ignore how narrow the allowed path appears to be. The universe permits complexity, but only under strict constraints. It allows stability, but only temporarily. It produces habitable worlds, but rarely and often briefly. Earth sits at the intersection of these allowances, not because it was guaranteed, not because it was chosen, but because it remained viable long enough to matter. This reframes the question once again. Perhaps the universe is not tuned for life. Perhaps life is tuned to exploit rare moments of balance. If so, Earth is not the target. It is the survivor. And survival, by definition, reshapes how probability looks after the fact. This does not dissolve the mystery. It sharpens it. Because if selection explains why we observe Earth, it still leaves open how many chances the universe had to produce such survivors and how fragile they truly are. Which brings us to a quieter realization. Earth may not be exceptional because it exists. It may be exceptional because it is still here, balanced, precarious, and not guaranteed to remain so. That thought leads naturally toward the next step. Not backward into probability, but forward into fragility. Because a system balanced on narrow margins is not defined by its past success. It is defined by how easily it could still fail. Earth is often described as resilient, Life survives disasters. Ecosystems recover. The planet appears to absorb shocks and continue forward. From a distance, this resilience can look like strength, as if Earth is robust, forgiving, difficult to truly disrupt. But that impression is deceptive. Earth is not stable in the way a solid object is stable. It is stable in the way a tightrope walker is stable, balanced, responsive, always correcting. Every system that keeps Earth habitable operates within limits. Temperature, atmospheric composition, ocean chemistry, orbital parameters, internal heat, all of them fluctuate, but only within narrow bands. Push anyone too far and the corrections fail. The planet does not resist change indefinitely. It negotiates with it. When temperatures rise, feedbacks pull carbon out of the atmosphere. When temperatures fall, volcanic activity slowly restores greenhouse gases. When ice spreads, reflectivity increases. When oceans warm, chemistry shifts. These feedbacks are powerful, but they are not infinite. They work only within certain ranges. Beyond those ranges, the same mechanisms that stabilize can amplify collapse. Warming triggers more warming. Cooling locks the planet into ice. Atmospheric loss accelerates once thresholds are crossed. Earth's history shows how close it has come. Global glaciations. Runaway greenhouse conditions narrowly avoided. Atmospheric shifts that nearly erased complexity. Each time, recovery depended on timing, magnitude, and the continued operation of stabilizing systems. There was nothing inevitable about the outcome. The knife-edge metaphor matters because it captures something subtle. Earth is not optimized for safety. It is optimized for persistence under constraint. The very processes that make the planet dynamic also make it vulnerable. Plate tectonics regulate climate but can trigger catastrophic volcanism. A magnetic field protects the atmosphere but depends on internal heat that will eventually fade. Liquid water enables life but also drives weathering that alters atmospheric balance. Every advantage carries risk. This means Earth's habitability is not a permanent state. It is a temporary condition maintained by active processes that will not last forever. The sun will change. The interior will cool. Orbits will shift. The balance will end. Not suddenly, not dramatically, but inevitably. Seen this way, Earth is not a miracle frozen in time. It is a moment. A long moment, measured in billions of years, but still a moment nonetheless. And that perspective changes how we interpret rarity. Earth did not need to be perfect. It needed to be just stable enough, for just long enough. That is a much harder requirement to satisfy, because it means survival depends not on one lucky event, but on continuous avoidance of failure across deep time, a sequence of narrow escapes, a long walk along a boundary where one step too far in any direction would have ended the story. Earth has walked that boundary successfully so far, but the knife edge remains. And that realization brings a final shift in tone. The question is no longer why Earth exists. It is why it continues to exist, and what that implies about the nature of habitable worlds in general. Because if Earth is balanced on a knife edge, then habitability itself may not be a state. It may be a phase, a temporary alignment that appears rare not because it is impossible, but because it is difficult to sustain. That thought leads us naturally to the last step, not to another mechanism, but to a conclusion. One that reframes Earth not as an accident, nor as a miracle, but as a fragile outcome in a universe that does not promise stability. And that is where the story comes to rest. When we look back at Earth as a whole, the picture becomes clear. This planet does not exist because the universe favors life. It does not persist because stability is common. It survives because a long chain of fragile conditions has remained unbroken. So far, Earth is not an endpoint. It is a passage, a narrow interval in cosmic history where balance holds long enough for complexity to emerge, reflect, and ask questions about its own existence. Nothing about this interval is guaranteed. Nothing about it is permanent. And that may be the most important realization of all. Earth feels normal only because we are inside it. From the outside, it is an exception layered upon exceptions, a world that avoided common failure modes repeatedly, not through perfection, but through continuous adjustment. It bent, it recovered, it endured, not because it was meant to, but because the universe allows rare islands of stability to exist, briefly, within overwhelming instability. This reframes how we think about habitability. Earth is not proof that life is common. It is proof that life is possible under strict constraints. The same forces that allow planets to form also work relentlessly to erase complexity. Habitable worlds are not the default outcome of cosmic evolution. They are temporary alignments, maintained against pressure from every direction. Seen this way, Earth is neither miraculous nor trivial. It is precarious, and that precariousness gives it meaning. Because if Earth should not exist, and yet does, then its value does not come from inevitability. It comes from rarity, from duration, from the fact that this balance has held long enough for awareness to arise. The universe did not promise this moment, it permitted it, and that permission may be fleeting. This does not diminish Earth, it elevates it. A planet balanced on narrow margins is not weak. It is remarkable for having lasted at all. Its history is not a story of guaranteed success, but of sustained avoidance of collapse. Earth exists not because the universe is kind. It exists because, for a time, the universe allowed a small region to remain calm. And within that calm, something learned to look outward, not to find purpose written into the cosmos, but to recognize how extraordinary it is that such recognition is possible at all. Earth may not be meant to last forever, but for now, it exists. And in a universe that does not favor worlds like this, that may be the most meaningful fact there is.